Hey everybody! Hey, welcome to Warp Zone. My name's Alex. I help coordinate events and help make this space a better place, I hope. And we have Steven tonight, who's also from our board. So we're board members of Louisville Makes Games, which is a nonprofit that tries to make game development a real career in the city. And we do that through events, co-working space that you're sitting in right now. We do that with kids education classes and now education classes for all ages and tutoring program, also a paid tutoring program that's available now. We have game jams, which are like events where, has anybody heard of a game jam before? Or a hackathon? So they're an event where you make a game in the course of a weekend, usually, sometimes a month, and you use everybody has the same theme to work off of, and you get into teams and you make something based on that theme. So we do those a couple times a year. We just had one global game jam, and there's another one coming up probably at the end of summer called Kentucky Fried Pixels, and that's our own personal game jam that we created here. And we have a game creators meetup, and that's the first and third Sundays of every month at 2 p.m. So if anybody's interested in making games, you can come back and check that out. We have playtest nights once a month. So if anybody's interested in playing games that people locally have made, we could really use playtesters, and those will be on the meetup page also. And yeah, so we try to promote all of the game developers who are making stuff in the city. Little studios have started to form. There aren't any big companies that you can go and just apply for a job as a game developer in our town. So most of the people are kind of starting from scratch and building their own thing. And so that's we're just a support system for that, and promoting it to everyone else. And so one of the things that we do in addition to all these events is we offer 24-hour access to the space for paid membership. And so if anybody is remote or wants to work or works remote already, wants to work from an office downtown, you can use it as your office space, and that's $100 a month. And you can ask me if you have any questions about that. And then, yeah, like Stephen was saying, all of our events are free and open to the public, so don't feel like you have to be a member for any of that stuff. It's all just public stuff. The membership does help us to keep the building or the space in the building, because we have to pay rent, so it goes towards that. And since we're a nonprofit, we just use all of that money directly to make the space better. And so we have got improvements to our space, like the projector and that kind of stuff, and couches and improved chairs and that kind of stuff. And then when times are tight, we just ask people to donate and tell them about our Patreon, where you can donate small amounts once per month, PayPal, where you can donate any amount anytime, and there's a tip jar on top of the refrigerator. And so now is obviously one of those times where times are a little tough, so I'm mentioning it. That's basically it. So yeah, so we have industry talks. We try to do them once a month. We're going to do an industry talk here at our space once every other month, but we're going to be the opposite months streaming what Run Jump Dev in Lexington has going on. So we're going to have a speaker here, a speaker there every other month. And so this is our first time where we're doing a talk here and they're streaming it. And then next month they're going to have a talk and we're going to stream it. So even on those nights where you can watch the live stream from home, feel free to come out and hang out with people. You can sit in here and watch on the projector, ask questions, all that kind of stuff. We don't have a specific date for it yet, but I think that it's going to be the same the third Thursday of the month each time, but we're not completely sure yet. So we'll try to make it a standard date so you always know. And most of the talks are going to be game development focused, and that can be kind of like anything, any topic that relates to game developers. So, so Stephen, what is your job title again?
It's something weird.
I read it and
it's cognitive / machine learning lead, but
yeah,
it's really, I just describe it as software developer.
Cool. So Stephen's got a great talk for us prepared. It's about artificial intelligence, and I'm excited to hear about it. Hear more about that. 9 years in the making.
Sort of, yeah.
Is that what you, or 2009 to now? Yeah, that's
Yeah,
it, basically. Yeah, so would you like to take over?
Yeah, thanks. Okay, so welcome everybody. What I'm going to tell you about today is, it's an artificial intelligence that I wrote about, about going on 10 years ago now, right before I had kids and then stopped having time to do fun projects. My oldest is 9. So what it is it's an AI that sort of learned to play a board game. And let me start with that. This is sort of the board that the game Mancala is played on. Has anybody ever heard of it, or anybody ever played Mancala? A few. Okay, yeah. So for those of you who aren't familiar with it, it's a turn-based 2-player board game like chess or checkers, something like that. And this is the board that it played. There are a lot of really cool kind of Mancala boards. You can find a lot of them are carved out of wood. It's a really, really old game. I probably should have looked up exactly how old, but it's quite old. And so been around a while. There are lots of different variations of it, but they all basically have this form where you have something like 12 pods. They're called buckets in the middle, and then 2 scoring pods at the end. And we'll get into the rules about it in just a second. But that's it. That's how this thing originated. I just did this in my spare time back, like I said, when I had such time to do such things. So let me show you what the game looks like. This was also back at a time when I had no idea how to make anything graphical, so it's all text-based. And then this is what the board looks like. If you can look back, and so again, there's 6 buckets in the middle and 6 buckets on each side in the middle, and then 2 scoring buckets on either side. And so here's what kind of mimics that. There's the 6 buckets on each side. Each of them has a number attached to it. The number it represents how many stones are currently in the bucket. And the object of the game is to take your stones from the board of play and get them into your scoring bucket. And there's some rules around that. Basically, the way that it works is you get to, on your turn, you get to pick one of the 6 buckets on your side. And when you do that, you scoop all the stones out of that bucket, and then you go clockwise, dropping 1 stone in each adjacent bucket until you run out. And that's it. That's your turn. So for instance, if I were to choose bucket 5 on this turn, I grab those 3 stones, I drop 1 in bucket 6, 1 in my scoring bucket, and then 1 would have to overflow to my opponent's side, and then he would take control of it. Or she, or it, in this case. Okay, so it'll be really good to have a pretty solid understanding about this, because I'm gonna move directly into some audience interaction. So before I move on, any questions about this? And I don't know if you can take questions on the live stream, Alex, but let me know if anything comes up there.
Sure.
I'll take an awkward sip of water. Give you guys a minute. Okay. Everybody feel relatively comfortable with this? Okay. So, now we're going to do something fun. I hope it's fun. Does anybody recognize this? Yeah, what is it?
Twitch plays Pokemon?
Yeah, Twitch plays Pokemon. Have you guys heard of this before? Okay, so Twitch is like a video game streaming service. You think of it kind of like a YouTube, but just for games. And typically it's done live. And so somebody had the bright idea to set up a game console that plays one of the Pokemon games, and then just let the crowd decide what to do by, submitting commands over here. And this is some of the fun stuff that happened. You just get somebody who's spinning around in circles because there's no hive mind. I mean, everyone has their own direction they want to go, and they're all tugging it in different directions. And that's kind of what we're going to do here in just a minute. So hopefully it doesn't turn out like this. I'll do my best to sort of guide everyone. So let's try it. As I mentioned, I wrote this some time ago, and much to my surprise, I downloaded a copy from SourceForge, where I had stored it, and the laugh that you heard is because of how long ago it was that people actually stored programs at SourceForge, and it works. I mean, this is like 3 operating systems later, it still works. So I'm going to take the suggestions here. We'll have one person playing, and I'll go ahead and have us go first. I'll make this a little bit bigger too. Is that okay? Can you just see that? Okay. Okay. So, as I mentioned, these are the stones in the buckets. We start off with 4 stones in every bucket, and on each turn we just get to pick one bucket. We distribute our stones, and then the AI will make its own selection, and then counter, and we'll just play until we finish it. So I guess I'll just start by shout out your choice for the first pick.
Bucket 3.
Okay, 3. Thank you. It always takes one to get started. So one thing to point out, it does keep track of which choice you made and then which choice your opponent made. In this case, the thing I'm calling Mancala-bot now. So, and you can see that you chose bucket 3, emptied it out, dropped one in each consecutive one afterwards, and then the AI chose bucket 5, emptied that out, and then dropped a few on, scored and dropped a few on to our side. So next.
2.
Thank you. Okay, chose 4. Now you guys can strategize if you want, or just try to be as disruptive as you want. That's okay too.
1.
But I will take the first suggestion, I think.
5. 4.
Okay, 4. And I'm happy to take suggestions from
I do have a question.
the live stream
We
too.
chose number 6 right now and it wrapped around. Would that score for the opponent as well?
Oh, good question. Thank you. No, it won't. I think there are some variants of the rules that do allow for that. In this one, it's just plain and simple. Like you score in your bucket, but if you wrap all the way around, it doesn't score for your opponent. In fact, you can't score for your opponent. So it just skips their scoring pod.
And ends up back at the beginning of your...
Yeah, so in this case, we grab these 9 and we drop 1, 2, 3, 4, 5, 6, 7, skip his, and then drop 1 here. So these would end up with 3 in them.
Bucket 2.
Okay, 2.
3.
6, is that what I heard?
Yeah.
Okay, now we get the wraparound. The AI did score there, but it's because he chose both 6 as well.
3.
I see a couple of different strategies forming here.
And then 4.
Okay. And don't worry, it's winning now, but we can still come back from this.
Okay, so I've played Mancala before, and just for strategy's sake, to clarify, if we end in our point bucket, we get to go again, right?
Not in this variation. Yeah. So there are so many variations, and I for those of you who were banking on that one and already are familiar with a particular variant, I am sorry.
No, if you land in your bucket, you do not get to take an extra turn.
Variant 2. If the opponent's buckets are empty, do we get all of the stones that are in our buckets?
I think that's the way this one works out. Yeah. Yeah. But to be honest with you, I didn't play test it enough to remember. Okay, 5. Eventually, see now he's in a position where he's been stacking up over here for a while, but now he's going to have to start spilling over into our side.
Right. 6.
And there it goes.
4.
Okay. 1. 2.
6.
I think I heard 2 6s there.
5. 6.
You're losing.
I mean, not that I'm rooting against you guys, but if it doesn't beat you the first time when you haven't played before, then, you probably shouldn't listen to the rest of the talk.
2. 3. 3. Yeah. 6. 4. 6.
Yeah, you guys are starting to see what happens here, right?
2. 5. I'm sorry. 5. 6.
2.
3.
I'll do those in order, 2 and 3.
1.
Okay, and it looks like we're in trouble now, right? We can finish this out, but it looks like he's got way more than us. So let me just go ahead and try to finish it out real quick here. In fact, yeah, he knows it now. And that, I hope that gracefully ended. That might have just crashed. It is really old software. So anyway, you guys get the idea, right?
Yeah.
Now
what happens when you pick one of the ones that was on our side that had 0 in it?
Oh, you can't.
Oh.
At least I think I guarded against that.
Alright.
Yeah. No, that's effectively skipping your turn, which isn't an option. Okay. So, I'm going to take a step back. We're going to come back to Mancala in a second. I'm going to take a step back to talk about AI generally. And AI is a thing that, I don't know if this is really true. I feel like it's in the news a lot lately, but that might just be because of how my news feed is filtered. What's on the board, does anybody recognize any of this stuff? Any of these symbols?
So that's IBM.
That's a wall light.
What was the...
The center's like an IBM.
Is that what's
Okay, you mean this guy?
Yeah.
Okay, so the guess I think was Watson. I am really surprised that anyone bothered to make a guess at this one. It's not Watson, but it's sort of something like that. In fact, I think it was made by IBM. You want to take another stab at it?
It's Big Blue, right?
It's Jeeves.
It's Deep Blue, yeah. Yeah.
Big Blue, Deep Blue, yeah.
Okay, that is the one that I expected no one to get. Yeah, is it on there? No.
I don't think so.
Okay, yeah. This is in a museum now, but Deep Blue, do you know what it is? You remember?
I'm kind of showing my age. Yeah, it was the computer that beat in chess the
It wasn't Bobby Fischer. It was,
Yeah, no, it was Garry Kasparov.
Yeah,
He was the 25-year world chess champion
Right.
from Russia, and he still plays occasionally, but long since gave up the title. But yeah, at the time was sort of right in his prime and absolutely and completely unbeatable, and this thing beat him, which was thought to be impossible at the time. Everyone knew that the engines were getting pretty good, but no one really expected this. And this was like late 90s. Probably should look up the year of that too. Anybody recognize any other ones? This one is Google's DeepMind symbol. And this one in particular is AlphaGo. These black and white dots are represent the board game Go. And it did a similar thing, though much more recently, because Go is a lot more complicated game than chess. Using what's called a deep learning model, it was capable of not only beating the world's masters, but it really advanced the game in a way that sort of changed how people played. It introduced a lot of new strategies, and I'm not familiar with Go enough to know exactly how it did that, but yeah, it really changed the way that grandmasters played. I don't even know if they're called grandmasters for Go. They are for chess, but yeah. This is the one that I thought someone might know. Does anyone know that one?
Is that the talking bass that you put on your wall?
It does look like Billy Bass, yeah. And in testing this talk, that is what my playtester said as well. But no, and it might actually be Billy Bass, but the specific symbol is it's Stockfish, which is it's also a chess engine, and it's kind of like the best, most accessible chess engine. You can go online and put in a position, and it'll make recommendations to you. And it's to give you a flavor of kind of how far AI has come. This match that Deep Blue had with Kasparov was pretty even. It was a very tight match, and the machine at the time was rated roughly around the same rating that he was. Today, 2000, whatever it is, 19, the top chess grandmasters are somewhere in the 2,800 range, and there are only a few. There are about 10 or so who are in that ratings range. The top engines are pushing 3,700, which to give you some appreciation for what that really means. On the one hand, there's absolutely no chance. The difference of that many rating points, of like 1,000 rating points, is something like the difference between someone who's never looked at a board and someone who's practiced for some time. And everyone thought sort of at the time, I say everyone, people predicted at the time that, oh, well, this is going to kill the game of chess. And in fact, of course it hasn't, because no human can memorize all the lines, and chess hasn't been solved yet, in the sense that no one's come up with, if you play perfectly, what is the outcome going to be? Like, for instance, in tic-tac-toe, you know that if you play perfectly, you can always get a draw. It's not like that with chess yet. It may be someday, but it's still too complex. And so what it's done is introduce a lot more strategies for humans to employ in their own games, and there's a lot of argument over whether that's a good thing or not, and whether that's made the game more or less interesting. But that's sort of the state of things now. So there are a lot of exciting things happening. The next thing that Google's more recently game related, Google applied the same kind of approach they did for AlphaGo to StarCraft. You guys familiar with StarCraft? Probably most everyone, yeah. And they made, I think it was called Alpha Star, and it of course is beating the best humans. And I'm sure that it will have a similar impact, right? Where we kind of learn something about what we've been missing. But the way it does that, and you'll kind of see this with how I get into building AI for Mancala-bot, is it just explores lots of different options, way more options than we have time to do, and then compares them against each other way faster than we have time to do it to come up with something that's that's better. So yeah, the next thing Google's trying to take on is a game called, I think it's called Hanabi or Hanabi. Have you guys played this one?
Yeah.
Okay, it's a card game, I think. I don't know that much about it, but the interesting part about it is so, and maybe Alex, you can correct me if I'm wrong about any of this, but you get a set of cards, and you get to see your opponent's cards, but you can't see yours, and you have to use sort of subtle communication clues like facial expressions and that sort of thing to communicate about what everyone has. And you can imagine trying to design a machine that is capable of doing that, but that's where they're headed. So lots of exciting stuff. Not quite to the point where they're going to take us over yet. I don't think we have to worry about that too much. I can tell you it's really, really hard just to get it to play a board game, but certainly interesting. So okay, so back to Mancala. Here's our board, and I promise there's a reason I made you go through the potentially painful exercise of yelling out bucket names. And that's so that we could understand what's valuable about the board. And I don't know if you can see the whiteboard here on the live stream, but I promise I'll say what I'm writing here.
See, like, to the projector this way.
Okay. So I'll do my best to call it out so folks who are watching can see it or hear it. But so when you're playing the game here, what kind of things did you care about? What sort of features of the board factored into your decision about what bucket to choose? Scoring, sure, right.
And not giving your opponent beats of things.
Yeah. Holding control of stones. Is that a fair way to characterize? Yeah. Anything else? I mean, in point of fact, those are the two primary things that matter, right? Anyone considering anything else while they?
Not wasting a turn.
Okay, so
Not making moves that don't score.
Okay.
Scoring on every move, basically.
Yeah.
Or revenge now.
Was that revenge?
Yeah.
Okay, I can capture that. Yeah, you can go to SourceForge and download it, and beat it. I will say one thing about this. It's the kind of thing that when I was finished with it, it came up with something that was pretty good, and it would be a novice for sure. But it's sort of like one of the old Nintendo games, where if you kind of find the glitch, you can find a way around beating it. It's sort of like a boss fight in that way. And if you, I won't tell you, if you really want to go try it out, it's kind of fun once you realize, oh yeah, I can beat this thing. But yeah, it's certainly not perfect, but it did come up with a darn good solution. So okay, so I've got score and very specifically scoring on every move, holding control of stones, and Alex really cares about revenge now. Anything else? Feel free to yell out if there's anything online too. Okay, so here's what I told the machine to care about. I'm skipping too far ahead. Okay, so obviously the score, right? The current score matters. In the board that I have featured right now, it happens to be that we have a score of 5 stones. And now I'm going backwards. Okay, control, also mentioned, right? In this case, I'm defining this as the number of stones in your buckets. So 7 plus 2 plus 3 plus 2. I promise there's not a whole lot of math here. And then I also define an extra feature that I don't know if it mattered that much, but I call it overflow. It's related to control, right? It's something like how many stones do you have on your side, but they're not going to stay on your side. So you can see, for instance, I got 2 stones in here, but one of them is definitely going to have to flip to my opponent. And same here, I've got 3, but one's going to have to flip over, and same here. So in this case, I call that overflow. And it's related to control, but slightly different enough that I felt like it might be a useful feature for the bot to consider. And so, how to form a strategy? Well, the way that I chose to do it is to just take each of these 3 features and assign it a number, a ranking between 1 and 10 or 0 and 10. And the rankings can be, decimals, because if there were only 1 to 10, there would only be so many to explore here. So, we can have anything like 8.12575 or whatever, but just for an example, we might weight the score at something like an 8 out of 10, and having control of stones at something like a 2 out of 10, and then we might rank overflow a little bit higher, something like a 3 out of 10. And so what that translates to, and the reason that's important to put a number on it, is because ultimately we're going to have a way to compare, is this board better for us than another board? Should we choose bucket 1? What's the result? And how do we compare the difference between those 2 boards? So we got to have some kind of number, some kind of way to compare them where everything's comparable. Yeah, question?
Is your score of 8, control 2, overflow 3, is that in relation to this current board? Like, where did the score 8 come from? Is that how many potential 8 based upon your current setup, or is that just an arbitrary number?
No, I should have just called this, instead of strategy, I should have just called this example. Just an example. One way that you might choose to rank these 3 features. You might choose to rank score as an 8 out of 10, control as a 2 out of 10, overflow as a 3 out of 10. I'll show you how that translates into a number.
In importance.
What's that?
8 out of 10 in importance.
Yeah, exactly. Okay. So I know that there's more math than I promised. Sorry about that. This really is the last slide with any math on it, and I'm sorry for the folks in the back. If you can't see it, what's going on here is, remember I ranked the score at an 8 out of 10, so I just multiply that by the number of stones currently in the scoring bucket to get a value for, like, how valuable is the score right now. Similarly with control, I take the ranking 2, multiply it by the number of stones I control, which is 14, to get, what's the relative weight of that feature. And then finally, there's a minus here because overflow is actually bad. So we add these 2 up and then subtract the overflow. And that gives us a number, 59. And you can attach a unit to it, call it 59 stones, but it's really just a number. It's just a basis for comparing, is this board better for me than another board or worse for me than another board? Did that get answering your question?
I see why it started stacking like 1, 2, and 3 now, as opposed to like when we were playing it, it was going on a higher end, and that's probably because like you start losing a lot of control when you start giving them a lot of things. So put them on, like in this case, 1,
Yeah.
as opposed to your 6.
Yeah.
That's probably where we made the worst mistake. Is we moved 6 when we had 10. We gave them essentially 7.
Right. Yeah, so one more thing to say about this. Oh, okay, so you guys have probably heard about the business of deep learning and deep whatever. That's not what's going on here. What deep learning is instead of us brainstorming and coming up with things to tell the computer to care about, like I tell you to care about the score or I tell you to care about the control, we kind of let the computer do that for itself, and that's a whole other topic that frankly I'm not that qualified to talk about, but I mean this is what uses the so-called neural network approach to to building an AI. I didn't do that here. I sort of simplified things by choosing for myself what the features are, but then I'm going to let the computer figure out how to rank those relative to each other. Okay, so. All right, so we have our valuation of the board. It's 59 stones. And then what do we have to consider? Well, if we look ahead, we can choose any of the 6 buckets and then run that same little equation on the new board that gets created by each of those 6 choices and then compare them all. And so, for instance, it might look something like this. If I choose bucket 1, I change from 59 to 74. If I choose bucket 2, I change the what I think the board is worth from 59 to 61 and so on. But then I have to consider what my opponent's going to do. And so for each of those 6 choices, my opponent might choose 6 things, and that's going to drop the value of the board for me. I mean, unless they're, unless they don't care or they're not that bright. So, really for each one of these 6, there's another branch with 6. I've only actually pictured 2 of them here. But you get the idea. It starts to expand exponentially. And I can go as many levels deep as, essentially I can go as many levels deep as my computing power allows me to go. Back in 2009, my machine let me go, I don't know, 4 or 5 levels deep. Certainly much more than a human can. And so I'm just representing one possible outcome here. And this kind of way of looking ahead, it's called a Minimax Strategy. It's just the idea is you minimize your opponent's good choices while maximizing your good choices. And so, if I only look to the second level here, I might say, okay, the best that my opponent can do is drop me down to 33. But on this side, he could actually drop me down to 5. And so even though the 104 looks nice and juicy, the counter move is really devastating. And so if I only looked the 1 level deep, I'd probably go here. If I look 2 levels deep, I'm probably going to avoid this because I'm going to assume that my opponent knows this. And I'm going to go here because the best he can do, I said 33, the best he can do is 29, right? But then if I look a 3rd level deep, it might really be the case that I have the opportunity to jump it back up to 95 here. Depending on how many levels deep you go, that determines sort of, that'll determine which choice you ultimately make. And so in this case, I would probably choose the 104. Another machine might value the board completely differently. I'm going to flip back and forth here. This is the strategy that we just walked through, but another strategy might have these values. And in that case, he has the possibility to end up at 82 down here and something less than 82 over there. So he might actually choose this bucket instead. He or she, or whatever you want to call these things. Okay, make sense? All right. This really has nothing to do with AI by itself. This is just to give you a flavor for what the computer is doing when it's deciding which bucket to pick. But that's just what any individual strategy will do. The real AI part is when you let the strategies compete against each other to figure out who's really the best. Because, yeah, sure, you might value the board at this, but the only way to find out if it's really good is to play against other things and see who wins. So, I'll show you how to do that next. Okay, so what's the motivation here? Remember we're talking about the values of the board here? And I said we give it a ranking. Well, you can come up with any kind of ranking that you want. And so the idea is, how do I search through all the possible rankings to find out which one's best? If I'm allowing numbers between 1 and 10, but I can go to any number of decimal places I want, there's quite a lot of options there, and we can't explore them all. So the real idea behind what I've done here is we just need a way to search. We need a way to do it kind of efficiently. In a case like this, where you want to search a really small space, it's super easy. It's easy for a computer. It's easy for a human. And it's easy to come to the best answer and know for certain that it's the best answer. Yeah, easy. So, but as the space gets bigger, it gets a little harder, both for humans and for machines. And eventually get to a place where it's actually either not possible to find the best, or it's so prohibitively expensive in terms of time that it's not worth it. You don't want to devote 100 supercomputers for a year of time to figure out what the answer is. You need something a little quicker, and that's what this does. And what is this? It's called a genetic algorithm, which I've already prepped you for this, but it's really just a fancy term for a search. It's just a way to search the space efficiently. And it borrows a lot of features from real genetics. The main components of it are, well, let's say I have a bunch of strategies, a bunch of ways to rank the board. How do I select which ones are the best? And once I select them, yes, how do I reproduce them? And then finally, there really also is a mechanism called mutation. It doesn't give them superpower. I mean, it kind of does, right? It makes them, ideally it makes them better. Sometimes it can make them worse. But this search really borrows heavily from actual sort of genetic theory. And so I'll talk briefly about what each of them really means. So here's how it works. I start with a pool of, let's call them bots, and all a bot is a way to rank those three features that we talked about. He has one way of ranking it, she has another way, he has a third way, and so on. And then I just let them all play against each other. And this might be the way that the scores come out. These three split their games with each other. This one wins all four of the games it plays with the others, and this one wins almost all of them. So one way to decide who gets to move on to the reproduction phase is to say, well, who won more? And that's a fine way, but it has a little bit of a problem in that if we just stick with these two, they're gonna really kind of dominate the strategy. And so if these two, for instance, really care about score, and they happen to beat these guys in this particular round, then they're gonna be overrepresented in the next round. And so instead of just purely letting the biggest winners move on, the approach is something like, okay, for each win you get a raffle ticket into the next round. And then I'm going to draw 2 tickets, and whoever's ticket gets drawn wins. So, if you win more, you're more likely to get to the next round, but certainly not guaranteed. And so, so when I select here, I might get this guy, and I might get this gal, and we might actually completely ignore the one with the most wins, and that's okay. The reason that's okay is because we're going to do this tens of thousands, hundreds of thousands of times, and over the course of all of that, we're going to produce something that's pretty good. And we don't want to ignore features that might be good against other bots by letting how they performed in just one round completely ruin their chances. Okay. So these guys move on. Okay, and let's say they look like this. This is not a real example. This is just a made-up example. But you can imagine that the one who cared only to rank the score at a 2 out of 10 might have been the one who only got 1 win. Let's give them names. Okay, so we've got these 2 bots. And the question now is, we're at the crossover phase. How do we use their rankings to produce something new? Well, anybody have any ideas on how you might do that?
Just add them and divide by 2.
Yeah, you could average them, right? In fact, that's exactly what I did. Right? So you just average them. Pick the midpoint between these 2 to get this one. Pick the midpoint between 8 and 6 to get 7, and so on. Helps to give this one a name too. Okay. So Miles is, I mean, in a real sense, it's the offspring of the parents, Les and Mara. And the mechanism by which you do this, I mean, you have some control over this. I happen to choose the average. You could do a weighted average. You could do whatever you want. That's part of the fun of this, actually, is tweaking exactly how you mix and match these things to come up with something that's useful. But average seemed like it was reasonable, and that's what I chose here. Okay, there he goes. All right, so the final phase here is mutation. And what's that useful for? Or what is it even? Well, like I said, this space to search is really, really big. And so if you start off with a pool, I think I started off with a pool of, say, 40 bots to play against each other. If you start off with that, one of them might be really, really good against all the others. Like, really, really good. And in that case, it's going to get a lot of raffle tickets to the next round, and it's also might get picked more than once for the next round, and you can see that it might actually just come to completely dominate. And what happens in that case is your solution converges really quickly to whatever this thing is, and you never get a chance to explore this vast space of possibilities. So how do you avoid that? You avoid that with mutation. So you can take one of the winners and kind of slightly perturb it a little bit to kind of jerk it out of whatever state it's stuck in, and give yourself some new options to explore. So you combine all these 3 mechanisms together, start with a pool of things, let them play against each other, decide who gets to move on, let them produce offspring, and then perturb those offspring a little bit to make sure that you're not getting kind of stuck in a rut, make sure that you explore all of the possibilities, or at least a reasonable number of possibilities, and you end up with some results. So here's what I came up with after running this. These are approximate numbers here, but this is kind of how, after 3 runs of this, and a run here was basically starting with a pool of 40, let them all play against each other twice, once where the first one gets to be first player, and then once where the other one gets to be first player. Let them all play against each other twice. Do the raffle ticket method to move on to the next round. Do the create the offspring. Do a little bit of random mutation. Only do it maybe 1% of the time. It doesn't have to be drastic, just something to make sure you don't get stuck in a rut. And let that run over, I think, 3-4 days on just a little laptop. And I did that 3 times, and these were the results. And you can see there's definitely some similarities, and I probably should have asked you guys where you think this should have aligned. There's definitely similarities where score looks like it's kind of honing in around a 6, and control is, there's a little bit of variability here, but definitely overflow is the least valued in all cases. I think if I were to run this again, I think, by the way, this is the one that you played against. So if you can find a better solution than this, I mean, enjoy. But what's the point here? Oh, yeah. So you can get lots of different outcomes, and it's precisely because there are so many possibilities. There's way more than you would ever have time to let your you can't come up with all the different strategies and let them all play against each other as many times as you want. There's just no time for that. So we employ this mechanism, and when you employ it and you introduce a little bit of randomness, you're going to come out with different results. I think when these played each other, this one was the best, and so this is why I went with this one. But yeah, you get a different result every time. And that is basically it. So I didn't give you guys really a chance to pause and ask questions. A couple of you did, but and that's a lot to go through. So any questions? Yeah.
Did you just do 3 or 4 days just because, or did you have like a loop that was like kind of running through, or how?
Oh yeah, good question. I think here's how I did it. Even with the crossover, and even with the mutation, you do start to see the pool of contestants converge onto something. And so I think what happened was I took the average of the entire pool after each round, and if the average didn't change that much, maybe within 0.001 or something, from round to round, then I just stopped. Once the convergence happened, then I'd say, okay, we're stuck here. We're probably not going to get out of it, and this is our best possibility. But there are lots of ways to do it. You can run a set number of rounds. You can, I don't know, there are probably other ways to do it. Those are the two that come to mind. Yeah. So other questions? Or any questions from online? Anybody want to see the code?
Sure. Yeah. Is it C?
I really did not expect anybody to say yes. I don't have it. I might be able to dig it up, and I don't know. Maybe you can post a link to it on the meetup or something if you guys are really interested. It is, to answer your question though, it was written in C++ actually, which is the thing that I knew at the time. It is the thing I don't know about anymore. No, it's been a long time since I used it. Yeah.
Would you do anything differently now that 10 years have passed and how you approach this?
Yeah. I would probably just watch Game of Thrones. No, would I do anything differently with the algorithm? If I were to do this again, yes. I would probably eliminate overflow. I think it's redundant. I don't think it's adding anything. So if it's just adding complexity without adding any value, just get rid of it. That's the first thing I do. You know, what I'd really like to do is try the neural net approach, where I don't tell it what features are important. I let it figure that out for itself and feed that back into the neural network.
Do you have any idea how that really works, like in regards to how it figures out that score in this case is important? Or I know like when they play like Dota 2 against each other, the same type of thing. Like, how does it even, what type of code or input do you even put in to say, figure this out?
Yeah, good question. I'm not going to have a good answer for you on that. No, it's, I can fumble around with an answer, but I'd rather give you a good answer, and I don't have it prepared. What I'll say is, okay, what I can say is, if you forget about the board games and think instead about something like the AIs that learn to play Mario games, the way those work is they just look at the pixels. What color is each pixel? Or what do the sprites look like? Or where they live or whatever. But it basically just takes a picture of the screen and then does some inputs. Usually the first rounds look like that Let's Play Pokemon Twitch thing where it's running around in circles. But the key is that it measures the progress. The one thing that it does get is feedback on whether it's making progress or not. And so you would have to find some way to tell this you're making progress. You don't tell it that, you don't tell it that pushing right on the control stick gets you towards your goal or anything like that. You don't tell it that jumping on a Goomba eliminates it from the field of play. You let it figure that out by dying, basically. And so you would have to do some kind of similar thing here. And beyond that, I don't want to try to, I don't want to get out of my league to try to answer that. Yeah, so other questions?
So does the control ranking, does that have to do with, like, the more control ranking that each one of them would have, does it have to do with, like, its ability to generate random numbers versus, like, what it would use to generate a number based on what the opponent is doing?
Okay, so
Kind of.
yeah, I think so. Let me go back to the how fast can I button mash? Okay. So, one more. All right. The way that the ranking translates to a number is you take each rank, but this isn't, I don't think exactly what I did, but it's something very close to this. You take each rank, multiply it by the value of each of these features, and then add them up to get just a number. So for any board, if I gave this guy any board, you could do this exact same thing. Figure out what the overflow is, figure out what the current score is, figure out what the control is, multiply them, add them up, get a number. With that number in hand, you can then look ahead at what would happen if I choose bucket 1, 2, 3, and so on, and do the exact same calculation. If I choose bucket 1, what would be my score? What would be the overflow? What would be the control? Do that little calculation to come up with a number there. And the same for each choice. And then do it all again. For each of those choices, there are 6 new choices, and again, up to whatever depth your computer will let you do it. And then after looking at all of that, you make a decision about what path makes the most sense by trying to maximize your final score while minimizing your opponent's.
So it is kind of like almost pretty much exclusively looking at what the opponent would do based on picking those numbers.
Oh, yes. Okay. So good question. In each of these cases, what's happening here is whoever's turn it is assuming that its opponent has the exact same value that it has.
Oh, okay.
Thank you for asking that, and I didn't clarify that on the first round clear. Yeah. What it's doing is saying, if I were playing against myself, this is what I would do. And, it's not playing against itself, so there's going to be some imbalance created in how each one values the board, and that's where we figure out
that's kind of
who's
how
actually better.
Yeah, okay. That's kind of how you get to where you want to get to as far as, like, the most ideal stats, or, like, get to a point of reaching the ideal stats that you want.
Yeah.
Okay.
Yeah.
So what's the highest score you can get?
You may call it the variation that I have. I started with 4 stones in each. I don't know. The real answer is I don't know. I mean, I was trying to think, like, can I even answer this? You start with 4 stones in each bucket. There's 4 times 6.
48 stones total.
Yeah, there's 48 total, but in
there's
point
no
of
way
fact,
you can't get 48 stones in.
No, of course not. I don't know. It's a good exercise.
I wasn't sure if your runs, like, found that, like, what was the upper boundary.
Got it. If it did, I didn't keep track of it. I only kept track of, like, what's the score.
Yeah. I figured when you got your convergence, those that you were maximizing your score too.
Yeah. I didn't. To give myself a break, this was when I was first learning programming, and I had no idea how to log things or anything like that. So, you know, I saved the final output, and that was basically it. And in between, it's like, hey, did it work or not? Did it give me the final output? Yeah, that's, I guess, to your question, another thing I would change is I'd really do some extensive logging of the in-between steps. Hey, where am I at after round 10? Where am I at after round 100? And, you know, how radically do things change, and how long do they take to actually settle in, that kind of thing. Be interesting to know.
How did you assign the values of like? You say you used 40 at first. Were those randomized, or did you just like pick the values of like your score, your overflow, and control? Where did those come from?
These?
No. Like the original players that started playing against each other.
Oh, how many bots?
How many bots do you start with, and then how did you? I'm assuming you assigned them some value in the beginning, or how did that work?
Okay, yeah. So, I started with. A lot of this boils down to, because there's a lot of choices to make here, and a lot of it boils down to what can your computer actually handle. To answer your second question first, how did I start? How did I get the first set of bots to play? Random number between 1 and 10. Just start with a random set, let them play against each other, and then see how it converges. So whatever you start with doesn't quite uniquely determine what you end up with, but it has a significant impact on it. So you can, like I said, you can run it several times and get several different answers, and that's why. To answer your first question, why did I choose 40? For a similar reason that I chose a search depth of like 5 or 6. And it's just because if I went any more than that, and it's a trade-off, you know. I could have maybe dropped the search depth to 2 or 3, and then I could maybe play with 80 or 100. You just kind of have to balance it and see how long is this thing going to take, and if it's going to take, you know, before I get my next job, then you got to do some adjustment. But that's basically what it was playing around with how long does it take to let this thing play against itself, and then just picking a number from there. Yeah.
So based on the scoring system you presented, and I know this is also for the presentation, so I'm not sure how directly it correlates to what was coded,
right.
But like say a robot or a bot for like with a 3-2-1 system would be identical to someone with a 6-4-2, just using scalars. Was there any handling for the identicality based on scalar multiplication at all?
Okay.
So like at the end, you showed the 3 winners and then still as a ranking of 3 numbers, but not what they would be if they were like a reduced, I guess I'll call it a 3-part fraction, just by ratio.
Oh, I see. I think I see. Let me see if I can capture that and tell me if I've got it. Theoretically, this could be anywhere between 1 and 10. So could this, and so could this. But did I put any constraints on, say, if the score is really high, maybe I can't let the control get too high? Something to account for what's the ratio between these things, and put some kind of constraint on it. Is that the question?
I think it's more just that you don't end up having identical bots in your sets. So say that one would be a little hard if we kept everything constrained to be no greater than 10.
Mm-hmm.
But your score 1, control 2, overflow 3 bot would be identical to your score 2, control 4, overflow 6 bot. Since once you divide by their greatest common factor, they reduce to the same ratio.
Oh,
between the two.
but they.
Because they would, while all the numbers would be twice as large, the importance of each board state would be the same in value.
I think I see what you're saying. I'm not sure if that's exactly how it would work out, though. Would it? No, you're right. It probably would. I didn't think about it.
And I was just wondering, especially when you show the results, and I was trying to do it quickly, but since at that point we were also,
Yeah.
we had 1 decimal place, if they reduced to similar ratios.
I want to think about whether that's actually true. I think you're right, but I would want to work through the example for myself. And even if it is right, no, it doesn't account for that. It just considers them different things. And then that's interesting though, because then when you try to, for instance, if you go to the crossover phase with those, you're going to get something kind of, I don't know, you would definitely get something different. And probably what that means is there's a little bit of a flaw in this model, right? In a sense, that's okay, because, you know, maybe you get something good out of that too. That's part of the interesting thing about this AI stuff is you don't really know what you're doing. Like when you get into this, you don't actually know what you're going to create. You don't know why averaging the 2 values is useful. You don't know how much of a mutation to give it and whether one is better than the other. And you actually don't have time to test all the possibilities either. So, you know, it sounds like it might be a flaw, and I think it probably is. But on the other hand, if I take it out and I sort of start to factor out things that are equivalent in that way, I might end up with a worse result. I don't know, I'd be curious to see.
I mean,
But if you kept them separate, then by the time they had a child, then you would end up with something completely different.
Exactly, and that might be a useful thing to have.
Right.
Yeah.
or also the other thing, if you had logged, you know, the results or whatever, and you were able to plot it and see, oh, these may be redundant, you'd have your answer right there.
Right, right.
So yeah, I mean, but to your point, like, yeah, you're not going to know what the full domain looks like until it's put into action, and then you got some data to do analysis on.
Right.
So, yeah.
How are we doing on time? Oh, we have plenty of time. So if there's any other questions, let me know.
How much memory does it take to run this?
The actual less than you'll ever care about. It won't interfere one bit with whatever you're doing. Yeah, because not only was this 3 operating systems ago, it was, you know, 3 layers of hardware ago too. So yeah, probably if I ran this now, I could expand it to something like 100 bots in a pool, and maybe do a search depth of 7 or 8 and get a hell of a lot better answer.
Do you plan to do any more with this?
Not with this particular thing. In fact, it was kind of strange that I resurrected it to give this talk from 10 years ago, but I do actually, I'm actually doing some studying right now at U of L, and I'm considering doing some kind of, you know, extending this to something else, something maybe even a little more fun, like some kind of, not Mario because that's been done, but maybe one of these guys' games or something. And there's always something to learn here. So when you just kind of get your hands dirty and start doing it, then you start to figure out, you know, really interesting questions. And sometimes you explore them and they're completely fruitless, but sometimes they're beneficial not just for the project you're working on, but they have applications beyond that too.
How long did it take you to create this?
Yeah, good question. I think it was about a couple of weeks. Yeah, something totally reasonable. I mean, you know, a lot of time spent on Wikipedia and Stack Overflow looking up this kind of stuff. But you know, once you're able to translate that into whatever language you're currently using, then it's really not. You know, I think the total amount of code is really small here. Yeah, I guess I will try to dig it up and post it for anybody who's interested. I'm sure it's sloppy, but you know, it did work.
some of the most exciting uses for AI that you'd like to see in the future?
Taking over the world. I just watched The Matrix for the first time, maybe since 1999. So now 20 years ago, with my kids. And I told them, this is going to blow your mind. And they said, oh, what, is he going to dive into the computer? And I was like, kind of, yeah. But yeah, there are so many things that I am so excited about, just for their own sake, for like, what's going to happen with chess? Is it going to be solved like checkers is? I didn't mention that, by the way. You know, I mentioned tic-tac-toe as a solved game. You know, if you have perfect play, what's going to happen? You're going to draw. Checkers is the same way now, and it's been that way since 2007. So, if you play perfectly in checkers, it'll be a draw. At some point, we might get there with chess. I don't know. We might get there with Go. And there are interesting kind of like toy applications of it too. There's the bot that plays ping pong. Have you guys seen that? Yeah. But there are also really, really, really cool actual, applications. Like, for instance, self-driving cars. I mean, those things use. It's not exactly like this, but they use an AI, like a iterative learning approach, to try to understand. Okay, if I'm driving in this lane, what's the likelihood that the thing I'm seeing there is the paint line versus whatever else it might be? And they've gotten really good at that. They've gotten arguably better than humans at that. And so those kind of things, especially for somebody like me, who I'm visually impaired, I can't drive. Those things are really valuable and useful, and they will be a great quality of improvement to our life right before they take it over.
I think Musk actually said that the Teslas will be fully autonomous by the end of the year.
Yeah, it's happening, I think, a lot faster than, than maybe the companies who were building it anticipated, or certainly than the public at large anticipated. But yeah, I'm super excited. Yeah.
Could you describe your research interests that you have?
I can, although not in too much detail because I really haven't gotten into it too much. But this kind of thing is fascinating to me, and there's just, even on this old project, there's so many interesting questions to explore. And now that I've been at this for a while, I think there's a lot of opportunity to do some basic things like remember what happened during the course of building it and log that and try to use that to understand something useful. And that's a vague answer, but it's kind of where I'm at with it right now. But yeah, I guess my hope would be that whatever it is I study, and it'll be in some way, shape, or form related to games. We'll also have applications beyond that. There's lots and lots and lots of demand for things like understanding what's in medical records, or what are in medical documents, like medical images and that sort of thing. And a lot of very similar techniques to this are what would be applied to that. So, yeah, lots of opportunity there. And there are a lot of healthcare companies here in town too who care a lot about that.
I have two questions from the stream.
Yeah.
The first one, were you able to figure out any optimal move sets from the AIs? What was the best one?
I should mention, Mancala, I think in most variants, is also a solved game. And it was even at the time that I made this in 2009. I didn't know that while I was making it, but afterwards I was very disappointed to look up and find out that it's already been solved too. And what solved means, by the way, is that there are two variations of that. There's weakly solved and strongly solved. Weakly solved is like, given the starting position, if both players play perfectly, you will know what the outcome will be. That's weakly solved. And I think checkers is such a game. strongly solved means from any position on the board, you know what will happen if both opponents play perfectly. And I don't think checkers has been strongly solved, but stuff like tic-tac-toe has. Even by kids in some cases, right? To answer this question from online, no. You'll have to remind me what the question from online was.
Optimal movesets.
Oh, yeah.
Missed one?
No, I didn't get. I'm certain that I never found that. I'm certain I didn't. Yeah. And the reason is because every time I ran it, I got something slightly different, and that tells me that it's not converging on a single thing. I didn't compare it against what is known to be the perfect play, so I don't know for sure, but I doubt it. I seriously doubt it.
And then there's a second question.
Yeah.
Are there any resources that you can recommend for learning more about machine learning algorithms and strategies for designing your machine learning models?
Yes, maybe. Well, there's so much now. There's so much. At the time that I did this, I actually didn't even know that it was machine learning. The term wasn't in my lexicon. I knew what genetic search was, and I knew I wanted to play with it. But but now, yeah, I mean, I guess what I would recommend is there are definitely a lot of online resources. I think what I would recommend is from really anyone from beginner to expert in programming would be to, and this is my bias because this is what I've been doing for the last 5 years, but to look into Python. There are probably Python or R would be the best language to familiarize yourself with, and you'll get differing opinions on that, and there'll be other people who will say Scala is the way to go, and it's sixes. But yeah, look into one of those, and the built-in package, in particular in Python, there's a package called scikit-learn. In fact, Google open sourced their package in Python. It's called TensorFlow, and they have pretty extensive documentation on it too. I haven't played with it, but it's there and it's available. And as far as sort of how to learn how to do that, I can't recommend specifically any like programs like Udemy or any of those, because I don't know which ones are good or which ones aren't. Here's what I'll say. The best way to learn, this is going to sound so awful, it's going to sound like my high school teacher, but the best way to learn is by doing. And so, I didn't know anything about this really when I started it, and it was just a bunch of looking at web pages. Hey, how does this thing work? Has anybody implemented it before? And Stack Overflow will have the answer. Yes, it has been implemented. It has been implemented in the language you're looking for, and here's the answer. So it's like if you start with a problem, something you want to solve, that's really the best place to start, and then you kind of figure out the individual components that lead up to that in their own kind of bite-sized chunks. That doesn't feel like a great answer, but I think it's the right answer, but it doesn't feel like a great thing to say to someone. But I don't know. Maybe feel free to continue the discussion. How to continue the discussion? Comment on the YouTube channel, I guess. For now, and I'll be happy to take questions afterwards too. If anybody has any more specific, like, hey, I'm looking into this resource, I could maybe offer some advice. Hope that helps. Okay, what else? Okay, well, that's Mancala-bot. I guess thanks for coming, everybody.
Thank you.
Thank you.